A hardwired control unit, HCU, is like a traffic light controller built from a fixed set of switches and wires. Each possible machine instruction has a dedicated path of logic gates that directly produces the required control signals. Register write, a LU operation, memory read, etc. A structure. Finite state machine, FSM, realized with flip-flops that hold the current state, often called the instruction decode stage. Combinational logic, such as AND or NOT multiplexers, that takes the present state bits and the opcode bits as inputs and generates the next state bits and the output control signals. Clock that synchronizes state transitions. Because the wiring is hardwired, the unit does not need a separate memory to store microcode. The logic is static. Once fabricated, the behavior cannot change without redesigning the silicon. This approach is traditionally used in very fast or low-cost CPUs, where the instruction set is simple and unlikely to evolve. A helpful analogy: imagine a set of railroad switches that are permanently positioned for each train type. When a freight train arrives, the switches are already set to guide it to the loading dock. There is no need for a dispatcher to decide each move. The hardware itself does the routing. A microprogrammed control unit, MCU, works like a small programmable robot that reads a recipe microcode and performs the steps one by one. Instead of a large network of dedicated gates for each instruction, the CPU stores a sequence of micro-instructions in a control store. Usually a ROM or RAM. Each micro-instruction contains the bits that directly drive the data path control lines and also a pointer to the next micro-instruction. A structure. Control store, an array of micro-words, for example 48-bit wide, that hold micro-instructions. Micro-instruction register, MIR, holds the currently fetched micro-word. Sequencer, logic that decides the address of the next micro-word. Next address logic, branch, jump, return, etc. Data path control lines, directly driven by fields extracted from the MIR. The MCU can be horizontal, many control bits, each directly controlling a data path line, or vertical, more compact, with encoded fields that are decoded to control signals. Because the behavior is defined by data microcode, changing the instruction set or fixing bugs can be done by rewriting the microcode, much like updating a software routine. Analogy: think of a kitchen robot that reads a recipe from a memory card. The robot's hardware, mixers, ovens, grippers stays the same, but the recipe can be swapped out to make a new dish without rewiring any cables. Gather the instruction set - list every opcode and identify the required control signals. For each phase, fetch, decode, execute, memory write back. Build the state transition diagram, STD-. Treat the control unit as a finite state machine. Each node represents a machine cycle, e.g. T0, T1, T2, and edges are triggered by clock pulses. The diagram shows how the unit moves from fetch to decode to the appropriate execute states for each opcode. Example: for an add instruction, the STD might be S0 fetch arrow, S1 decode arrow, S2 read register A and B arrow, S3, LU add arrow, S4 write result arrow back to S0. Assign state encoding - choose a binary encoding for each state, e.g. 3 bits can encode up to 8 states. Minimize the number of bits to reduce gate count. Derive next state logic - write Boolean equations for each next state bit as a function of current state bits and opcode bits. This is done using Karnaugh maps or a logic minimization tool. Derive output control signal logic - for every control line, e.g. reg write, ALUOP mem read, write a Boolean function of the current state and opcode. Example: reg write equals S4. ALUOP equals opcode equals ADD and S3. Synthesis - convert the Boolean equations into a gate-level netlist and or NOT multiplexers. Tools like Verilog synthesis will automatically generate the optimal gate implementation. Clock register implementation - use D flip-flops to store the state bits. The D inputs are the next state functions. The clock drives synchronous updates. Verification - simulate the FSM with all opcodes checked that the generated control signals match the intended timing. Key takeaway: hardwired design is analogous to drawing a flow chart STD, then translating each branch of the chart into a fixed set of logical switches that fire automatically on each clock tick. Design steps for a microprogrammed control unit. Define the micro instruction format, decide the fields needed. A typical horizontal format might be: opcode field, for example 6 bits, identifies the macro instruction. Control field, for example 32 bits, each bit directly drives a data path line such as register write, ALU operation, memory read, and so on. Next address field, for example 8 bits, address of the next micro word. Branch condition bits enable conditional jumps based on status flags. Organize the control store. Choose ROM for fixed microcode or RAM for writable, updatable CPUs. Calculate size as number of micro words multiplied by word width. For example, 256 micro words times 48 bits equals 12 kilobytes. Write microprogram for each instruction. Break every machine instruction into a series of micro steps. For add, step 1 load register A, set read A equals 1, instruction register to 0. Next step 2 load register B, set read B equals 1. Next step 3 perform ALU add, set ALU operation to add. Next step 4 write result, set register write equals 1. Next go to fetch. Design the sequencer logic. The next address is often a combination of a sequential address, program counter plus 1, for straight line flow, a branch address when a condition bit is true, for example 0 flag causing a branch to microcode for a conditional, and an opcode derived start address for the first micro step of a new macro instruction. Implement the micro instruction register, MIR. On each clock, the MIR loads the word from the control store at the address supplied by the sequencer. Decode control field. Directly fan out control bits to the data path. If using a vertical format, add a small decoder that expands encoded fields into actual control lines. Testing and simulation. Run the microprogram with all opcodes and verify that the sequence of control signals matches the intended behavior. Analogy: think of a DVD player that reads a list of commands such as play, pause, forward. The player hardware, laser, and motor stays constant, but the command list can be edited to add new features. The microprogram is that command list, and the sequencer is the DVD player's tiny computer that decides which command comes next. Key point: microprogramming separates what the control does, the microcode, from how it does it, the fixed sequencer and decoder. This makes the CPU much more adaptable. Cycle time and throughput comparison. Parameter hardwired control unit, microprogrammed control unit. Critical path, usually short because only combinational logic between state registers and output gates. Example: 10 picoseconds gate delay times 5 levels equals 50 picoseconds. Longer because the path includes fetching a micro word from the control store, decoding it, and then generating outputs. Example: ROM access 30 picoseconds plus decoder 15 picoseconds plus gate delay 5 picoseconds times 2 equals 55 picoseconds. Clock period: T clock equals T logic plus T setup plus T hold approximately 70 picoseconds. For the microprogrammed unit, T clock equals T ROM plus T decode plus T logic plus T setup plus T hold approximately 110 picoseconds. Throughput instructions per second. Assuming 1 cycle per instruction, 1 divided by T clock is approximately 14.3 GHz. For the microprogrammed unit, the throughput is approximately 9.1 GHz. Multi-cycle penalty. If an instruction needs more than 1 cycle, for example memory access, the same fast clock is used, so overall CPI may be slightly higher but still benefits from the fast T clock. For the microprogrammed unit, each microstep still consumes the longer clock, so CPI is higher. Numerical example. Consider a simple 4-stage pipeline where each stage is controlled by the control unit. Hardwired stage latency equals 70 picoseconds, so the pipeline clock is 70 picoseconds. Instruction latency equals 4 times 70 picoseconds, which is 280 picoseconds. Throughput equals 3.57 GHz. Microprogrammed stage latency equals 110 picoseconds, so the pipeline clock is 110 picoseconds. Latency equals 4 times 110 picoseconds, which is 440 picoseconds. Throughput equals 2.27 GHz. Interpretation. Hardwired units provide higher maximum frequency, but microprogramming adds flexibility at the cost of a slower clock. Formula recap. Cycle time, T clock equals maximum path delay plus setup plus hold. Throughput instructions per second equals 1 divided by CPI times T clock, where CPI is cycles per instruction, often 1 for single cycle designs. Flexibility when adding a new instruction. Scenario 1: Hardwired control unit. New instruction. MUL R1, R2, R3 multiply R2 and R3 store in R1. What must change? Add a new state or reuse an unused state in the FSM for the multiply operation. Extend the state encoding more flip-flops if no free codes exist. Design new combinational logic that, when in the MUL state, activates the ALU op equals MUL line, enables the two register read signals and later the register write line. Refabricate the silicon or redesign the FPG a bit stream. Analogy, adding a new road to a city that requires digging new tunnels, laying fresh pavement, and installing traffic lights. A costly, time-consuming process. Scenario 2, Microprogrammed Control Unit. Microcode additions. Write a few micro words that perform the same steps as the hardwired design. Fetch operands, select a LU multiply, write back. Place these micro words at a new address in the control store and update the opcode to micro address table, often a small ROM, to point the new opcode to the first micro word. No hardware change, only the contents of the control store or a tiny ROM are altered. Analogy, adding a new dish to the kitchen robot's recipe book, the robot's hardware stays unchanged. You just upload a new recipe. Case study, adding XOR instruction. Hardwired requires adding an XOR gate into the ALU control line and a new state to enable it. May need extra wiring. Microprogrammed, only a micro word with a LU op equals XOR field set to 1 is needed. The existing ALU already supports XOR if the control field is present. Result, Microprogrammed Control Unit wins in flexibility and time to market, while hardwired may still be preferable for extremely high speed or area-constrained designs. Memory versus gate count trade-off. 1. Control store size. Suppose we have 256 micro instructions, each 48 bits wide. Total memory equals 256 times 48 equals 12,288 bits, approximately 1.5 kilobytes. If the control store is implemented in ROM, the area cost is roughly a ROM approximately 0.5 square micrometers per bit, approximately 6,144 square micrometers. 2. Hardwired gate counts. For the same instruction set, assume we need 6 state bits and 30 control output bits. Using Karnaugh minimization, the average Boolean function for a control line may need 3 to 4 2-input NAND gates. Rough estimate: 30 outputs times 4 gates equals 120 NAND gates. Each NAND gate occupies about 0.1 square micrometers, approximately 12 square micrometers total. 3. Quantitative comparison. Design table with columns: design, memory bits, approximate area, gate count, approximate area. First row: microprogram design 12,288, memory bits 6,144, ROM plus 200 address, decoder approximately 6,344, area dash dash. Second row: hardwired design dash dash 120, NAND gates 12, area. Interpretation: the microprogrammed approach needs orders of magnitude more silicon area for the control store but vastly fewer logic gates. In modern deep submicron processes, ROM area is cheap relative to complex combinational networks, so designers often accept the memory cost for the flexibility gain. Cost perspective: if a chip costs 10 cents per square millimeter, the extra 6,332 square micrometers, approximately 0.63 square millimeters, adds only 63 thousandths of a cent per die, virtually negligible compared with overall die cost. Takeaway: memory-based control stores shift cost from gate count, area, and power to storage cells. The choice depends on design priorities: speed versus flexibility versus silicon budget. Problem: design the control signal generation logic for a single cycle add RDEST, RSRC1, RSRC2 instruction using both a hardwired control unit and a microprogrammed control unit. Section: a hardwired design. Step 1. Identify required control signals. Reg read A, enable read of RSRC1. Reg read B, enable read of RSRC2. ALU op 3-bit set to code for add EG010. Reg write, enable write to RDEST. Result cell, choose ALU output for write back. Step 2. State encoding single cycle, so only one state S0 is needed. Let S0 equals 0, 0, 0. Step 3 Boolean equations. Since only one state each control signal depends solely on the opcode bits, for add say opcode equals 0, 0, 0, 0, 0, 1. Reg read A equals opcode equals 0, 0, 0, 0, 0, 1. Reg read B equals opcode equals 0, 0, 0, 0, 0, 1. ALU op bits 2 to 0 equals 0, 1, 0 when opcode matches add. Reg write equals opcode equals 0, 0, 0, 0, 0, 1. Result cell equals 1 select ALU output. Step 4 Gate implementation. Use a 6-bit decoder for the opcode. The line corresponding to 0, 0, 0, 0, 0, 1 called DAC ADD goes high. Connect DAC ADD directly to Reg read A, Reg read B, Reg write. Feed DAC ADD to a small constant generator that drives ALU op equals 0, 1, 0 hardwired via 3 NAND gates producing the pattern. Step 5 Result 1 combinational block decoder plus a few gates produces all control signals in a single clock cycle. No next state logic is needed. Section B Microprogrammed Design. Step 1 Micro instruction format horizontal 32-bit control field plus 8-bit next address. Bits 0 through 3 Reg read A. Bits 4 through 7 Reg read B. Bits 8 through 10 ALU opt. Bits 11 through 12 result cell. Bits 13 through 14 Reg write. Bits 15 through 31 unused reserved. Step 2 Microprogram for add single micro step, because we assume a single cycle data path. Micro 0 address hex 40 control word Reg read A equals 1 Reg read B equals 1 ALU op equals 0, 1, 0 add result cell equals 1 Reg write equals 1 next address equals fetch e.g. hex 0 to start next instruction. Binary representation example 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 1 illustrative. Step 3 Opcode to micro address table entry for opcode 0, 0, 0, 0, 0, 1 points to address hex 40. Step 4 Sequencer operation on instruction fetch. The opcode is decoded, the sequencer loads the micro address hex 40 into the mirror, the control store, outputs the 32-bit control word each field, directly drives the data path signals after the micro step. The sequencer jumps to the fetch address ready for the next instruction. Step 5 Result no combinational logic beyond the small decoder for the opcode, and the control store read path, updating the add definition, e.g. changing to a saturated add, would only require rewriting the micro word at hex 40. Comparison summary aspects hardwired versus microprogrammed logic depth hardwired, fixed often 2 to 3 gate levels, microprogrammed 1 extra ROM access plus decoder slightly deeper design, effort hardwired write Boolean equations minimize synthesize microprogrammed write micro words, build address table changeability hardwired, requires new hardware or array programming FPGA, microprogrammed simply edit microcode area hardwired few gates no memory microprogrammed. Control store ROM plus small decoder speed hardwired typically a few picoseconds faster, microprogrammed slightly slower due to ROM fetch. The answer demonstrates how the same instruction can be realized in 2 opposite philosophies, a direct hardwired wiring of control signals versus a programmable microcode recipe.